Sure. So I will have to do the introduction myself. I'm Mark Leverett. I'm going to talk about designing large-scale applications in Python. I've pretty much done that for more than 10 years now, so I gathered a bit of experience in that field, and I hope to give you some feedback on what can be done, what should be done in some cases, and what you should try if you want to design large-scale applications as well. The talk is probably a little longer than an hour. I'm not sure if you're okay. If you want to do more than an hour, we have some space into the break. If you prefer not to do that, I can also offer to do a breakout session in the open space. So when I'm reaching the last part of the talk, I'm going to just ask you, and then we can see how it goes. Okay? So a bit about myself. I'm working for eGenix. I'm a consultant. I help companies write large-scale applications. I've been doing that for many, many years now. Some of you may know me as the author of the MX tools. I pretty much wrote all of those. eGenix also sells products in the Python space, which is a bit uncommon. Most of the stuff that you get for Python is open source. Because we also ship open source software, we have to fund the development for that somehow. So that's why we have MXODBC and the related database products. And that is also what we charge for it. The agenda is very simple actually. It's just an introduction. Then I'm going to talk about application design. That's going to be the biggest part of the talk. And then we have section 3, which is before you start, and that's where I'd like to ask you whether you want to continue or not, because I'm not sure how long it's going to take to reach that point. Okay, let's start with the introduction. As you all know, or probably know, Python is very easy to use. It's very easy to write applications. Of course, if you make it very easy to write applications, it's also very easy to write bad applications. And it's very easy to write bad designs. So, in general, when you're working with Python, you always have to consider going back again to the code and refactoring it, or maybe even rewriting larger parts of it. Python makes that easy as well, so it's not a very serious situation. In fact, you should use that approach more and more often to get better code. As a result of that, the application design in the project that uses Python becomes one of the most important factors, especially success factors. Because if you write a large application that has many thousand lines of code in Python, you can easily end up creating a huge pile of mess that is very hard to get right again and to make maintainable again. Because in the end, you're going to, even though Python is easy to write and it's also easy to understand, you're still going to create something that is very hard to maintain, because there are so many things in Python that you can do, so many tricky things that go on behind the scenes, that it can be very hard to maintain the resulting code. So you have to be careful when doing that. What I'm going to present is a very general approach to application design. It may also apply to other areas and other languages. I can't really say, because I'm mostly working with Python and C, and that's about it. So I'm not doing any Java developments or anything in that area. Right, so what's a large-scale application in Python anyway? In other languages like Java or C, you usually talk about millions of lines of code if you're talking about large-scale application. A lot of that is usually boilerplate code. In Python, the scale is a bit different. It's about an order of magnitude lower than in Java or C. So what I consider a large-scale application is, for server applications, it's at least 100,000 lines of code, which is quite a lot if you write Python. For client applications, it's a bit less. It's around 50,000 lines of code. And if you have ever written a larger application in Python, then you probably know that you're using lots and lots of third-party code in there. So you usually download lots of stuff from the web, install it, and use it in your project. So you don't have to rewrite all that. But of course, that counts towards those figures that I have here. And if you want to speed up your project in a few areas, then usually you also use C extensions. So the projects themselves are usually mixtures of Python and C. And typical examples that you probably all know are Zope and Clone. Whereas Clone is basically running on Zope, it's just using the Zope as platform. Things you probably don't know is the eGenix application server that it's never gone public. It's only being used in projects. And we've done a couple of projects that have been in this kind of area, using large-scale applications. The latest one that we've worked on for a customer is an ASP trading system. So it's actually a complete trading system written in Python. So why would you choose Python as implementation language for writing a large-scale application? Well, first of all, it's highly efficient. It's basically the language of choice for small teams. If you have a small company and you want to write an application, you want to develop quickly, then the only way you can do that successfully is by using the most efficient tools that you can get. And Python is very good at that. So you can have a small team, and the small team can easily compete against larger companies if they use, for example, Java or C. It's also very competitive in that it allows you to produce software quickly, it allows you to adapt to changes in the industry quickly, which is becoming more and more important. Today you don't have the situation anymore that you write a huge specification for an application and then you write the software and then you're done. It usually happens that while you're developing the software, while you're implementing it, the requirements change because the industry changes. So everything is moving very quickly. And to adapt to that, you also need to use something that can easily be changed, that can easily adapt to the new situation. That's also important when you look at the design from the start. You have to be careful not to fix yourself in any way. You have to always stay flexible, because you cannot really know whether the customer wants a change halfway through the project. And we've sometimes had the experience that we had to make major changes to the application simply because the way that we understood things, or the customer understood things, simply didn't work out for what the market actually required. So it's important to have flexible tools. The design concept that we use for doing this is based on two things. One is a structured approach. It's actually a top-down approach. So you use this principle, divide et impera, which is divide and conquer. If you studied computer science, you probably know. It's a very common way of approaching complex projects. You simply take the whole thing, break it down in smaller parts, and you continue that recursively until you've reached a level where you can actually manage the code that you have to write there. So what we do is we first look at the different models that you have for application design. Then we try to break those models down even further using Python objects. And we do that until we reach a very low level, which is the data and task objects. And that's what I'm going to talk about in the next few slides.
Excuse me, you published these slides?
Yes. Yes. That's something I forgot to say. If you have any questions, just ask, please. Because the talk is a bit complex sometimes, and if you don't understand something, it's important that you just not just raise your hand, just ask. I'm going to publish the slides on the net. The slides do contain a lot of text, which you should normally not do when you write a presentation. But I thought it would be better to have more text on the slides, so that when you download the slides, you can actually still understand them, rather than just having a few taglines there on the slides. Right, so we had the structured approach to application design. The other thing that you have to consider is you have to have a set of guidelines, very much like the Zen of Python. You know that? If you import this, you get this list of this bullet list of the Zen of Python that Tim Peters originally created. And if you use such a set of guidelines, then it often helps you when making decisions in the application design. So there are several things that, well, very common things that you probably all know, like the KISS principle, keep things simple but don't make it any simpler. The other important one is the DRY principle, which basically means don't repeat yourself. So don't do anything, or try not to do anything twice. If you have a need to do something twice, it's often better to refactor your code, so you only have to write it once and you only use it twice. The next few things are needed when you try to break down the components into smaller parts. So if things start to get too complex, what you usually have to do is you have to add some form of management to your code. The other thing is, if management doesn't even make it possible to handle your code, you have to continue breaking down parts. So you have to use decomposition. And something that's very important is that there's actually beauty in design. So if you write code that looks ugly, it's probably a bad design. So you should probably go back again, try to refactor it, try to make it more intuitive and easier to read. So those are the principles that we use for doing this. Yes.
What do you mean by management? On the previous slide.
Management. I'm going to talk about all these things in the next few slides. So management basically means that if you have to work on a certain task or a huge number of objects, then you have to group those objects in some way, and you have to manage those objects. So you have to provide a central point of access to the objects. So what I'm going to do now is I'm going to look at all the different levels that you have in the design process, from top to bottom. So I'm going to start with the application model. So the first choice you have to make is you have to find the right application model for the application that you want to write. There are several different application models that you can use. Very common ones are client-server applications that have a client part that runs on a desktop somewhere or on a web browser. And then you have a server application, and the client communicates with the server application over some network or even using RPC on the same machine. The other approach is a standard GUI approach, where you usually use a multi-threaded application. So you have multiple threads running. You don't have this client-server separation. And you can also have a single process where you do command line processing. So there are many ways of implementing your application model. When choosing an application model, you always have to think about the implications regarding the performance of the application later on, the scalability. So if you want to write an application that needs to be scalable, or very scalable, then it's usually better to have some form of client-server application. The next step is choosing the processing model. Processing model basically means how you structure your the way that you implement the processing of requests coming into the application. So you have various different models there. You have a single process model. You have multiple processes, which is what you often use if you use a web application. For GUIs, you usually use multiple threads. You don't want to bother with multiple processes. It also depends a bit on the platforms that you're targeting. For example, if you're writing an application that needs to handle multiple tasks at the same time, on Unix you'd probably use a multi-process model, whereas on Windows you'd probably use a multi-threaded model. There are several implications with that as well, like for example, if your application crashes and you have a multi-process model, then it's not really such a bad situation, because only one process will get killed by the OS, for example, if it uses too much memory. If you have a multi-threaded model, then the whole application will go down if something goes wrong. So that's something that you always have to consider.
Just on that distinction between multi-process models and multi-thread models, I'm not sure the using multi-processing on Unix, using multi-threading on Windows really holds so much for Python, because Python processors have such a I mean, you can't do the whole fork and process in Python because the Python interpreter takes so long to initiate it. So I'm not sure it's that distinction still with Python.
Well, it is true that the Python interpreter does take a bit long to start up. What you usually do is you pre-start the processes and then you just use them. So
I think performance-wise, then it ends up about the same on Windows or
I'm not sure. I mean, Windows is very much optimized towards threads, so it's very fast in doing threads. If you look at the task switching between processes on Windows, it's much slower than on Unix. At least that's what our experience is with processes on Windows. So it's not only on Unix, for example. It doesn't really matter whether you use a thread or a process. Is more or less the same thing, performance-wise. On Windows, we found that threads is much more efficient there. But maybe your experience is different, so maybe things have changed in the last year. I don't know.
I find that I've had to use threads on Unix with Python purely because of I mean, you can have multiple processes, but you can't do the whole forking logic like you do in Apache.
Why can't you do forking? OS don't fork, it exists in the process.
Yes, but it takes a long time to start the Python process.
But no, it doesn't start the Python process, it just forks it. I mean, OS.fork is simply an OS level fork. Nothing else. You don't need to start a new Python process, you just fork it.
Okay. I was in this game.
That's like in C.
There are some issues with fork, but in general, that's what we usually do. We use multiple processes on Unix because it's a lot more stable. If something crashes, you just have one process going down, whereas with the multi-threaded approach, you have the whole application going down. And in some cases, it's very important, especially if you use third-party libraries, because some third-party libraries that you have to use, numeric libraries or whatever you have there, they sometimes have memory leaks, for example, or there are certain situations where they can crash, like division by zero errors or these things in the C. So you get well, the application crashes, and then of course you don't want your whole service to just go down because of that. Right. So the next thing to consider when choosing the processing model is you have to define boundaries between the objects that you're using in the application, and you have to ask yourself a number of questions. For example, which objects do you have to have access to the same object space? So you usually want to have all of those in the same process. Or you have to ask yourself, where is state kept? Do you keep state in a certain number of objects in your process, or do you keep state in a database, for example, or do you put it on the file system as pickle and then load it again? And finally, something that you probably would not really consider is you have to decide what defines an application instance. The meaning behind that is if you use a design like this, like what I'm going to present here, it's actually possible to have the whole application as object. And then if you need more of these application instances, you can just create a new object and then you have a new instance of your application running there, which can be very useful. For example, if you want to have one thread per application instance. So we've done the application model, we've done the processing model. The next thing is the layer model. So when you write an application, you can divide it up into layers from top to bottom. By the way, back there, can you hear me? Yes? Thanks. You usually start with the interface logic as the top level, and then you work yourself down to the very low levels where you store the data and you do all the processing in between. Depending on what you're writing, it's usually very straightforward to define those layers. So for a GUI client application, you have the GUI, you have the application logic, you have a storage layer. It's very simple. For web applications, things tend to be a bit more complicated. Plus, there are more areas of problems that you have to address. On the client side, you usually use a web browser. Then you have the network, which introduces another set of problems. Then you have a web application server, which is usually uses Apache normally or Lite, and then it interfaces to your processes using some form of interface logic. In the old days, you use CGI for that. Nowadays, you can also use smart Python for that if you want to just address Python. We found that it's better to use SCGI for that because it allows you to create more stable applications. Because, I don't know, does any one of you know SCGI? No one. You should really look that up.
No, but I had problems with proxy.
Who was that? I didn't see you.
I had problems with proxy.
With proxying?
Yeah.
Well, you do have to set it up correctly, but once you've done that, it should work. So we've been doing exactly that. So we've been using proxying as well, and it works out really well. What SCGI basically does is a very smart way of doing CGI. So you use the fact that on Unix you can actually copy file descriptors, and what you create when you start off a new process, you fork and then you copy the file descriptors. So what you get is you get a direct pipe from the main process that Apache is talking to the process that's actually handling the requests. And there's a mod CGI for mod SCGI for Apache you can download, and there's a corresponding Python module that you can use in your application. Another approach is using Whiskey. Can't say anything much about that because we haven't used it, but it seems to be more or less the standard now for doing Python applications. So maybe that's the better way of doing things for you. Once you're in the application, of course, you have to provide all the server logic. You have to decode the requests. You have to set up response objects, and then you have to write your application logic and storage logic again, like what you already have for the client application. For batch processing, things are a lot easier. You just have file I/O, and then you do the same thing again. So I'm going to give an example using a web application. It's a very standard scenario. So what you use is you use a web browser as a client. You know that the server is going to have a lot of load. It's going to have a lot of things to do. It will have to do a lot of calculations. It's very important for the server to be fail-safe, so in case something goes wrong, it should just continue working, even though maybe one request fails, but the other request should not. And the server is connected to a database. So if you apply the different model decisions here, what you'd normally do is you use a client-server application model for that. For the processing, because you want it to be fail-safe, you use a multi-process model. And for the layer model, you just use the standard kind of layer model that you have for these applications. Right, so now you have the layers. So you've broken down your application already into smaller parts, these layers. But implementing those layers is usually hard to get right. So what you do, again, divide ad impera, you break things down. And the way that we break things down is we use components for that. So we have a look at each layer, and then we try to create components that implement the logic that's needed for these layers. the way that we do this is we use a loosely coupled component approach. So what we try to do is we have multiple objects, each object representing a component, and then we define certain interfaces between those components. We don't use things like what you have in Zope, for example, the Zope interfaces, because we think it's not really needed. Python is already very good at doing interfacing, and doing interfacing by introspection works very well in Python. And it's really just adds another level of complexity if you add the interfaces there. Some people may feel more comfortable by having interfaces because then you can actually have some form of type checking, well, interface checking in that case. So if you plug in new components, you immediately know whether the component will work with the system or not, depending on those interface checks. The way to approach this component design is to have a look at the various concepts that you have in the application. For example, in the web application, you want to have a component that deals with all the request decoding, and you want to have another component that deals with all the response encoding. So you have to look at the various concepts that you have in these layers, and then for each concept that you have in the layer, you create a new component object. And then you plug them all together later on using something that you call a system component. I'm going to talk about that later. So typical examples of component are, for example, for the database interface, you want to have user management, you want to have session management, you have caching, you want to interface to a database, so you probably have some kind of database abstraction layer there. So you have a component for that as well. And you have general facilities like logging that you need in the whole application. You'd also write that as component, even though those components will not really fit into the layer model. They sit a bit along the side of everything. The main advantage of using component objects for these things is that they are easily replaceable. So if you find that you've implemented a component that doesn't really work that well because the design is not right, or because the requirements of the project have changed, what you want to be able to do is you want to be able to easily rewrite the whole thing without having to change the whole application. So what you try to do is you try to define a proper interface for these components, and then you want to be able to just rip out the component that you had and replace it with something else. For example, we had in a situation where we had to change the database component of an application, and because we just had the interface defined for the component, we can easily just take out the old component, write a new one, in that case based on a SQL database, and then plug it into the application and it just works, without having to change anything else. If you do this right, then you can also later on change the processing model. So you can, for example, go from a multi-process approach to a multi-threaded approach if you have to. Simply because everything is an object and you can just plug them together. And using this application instance, you can have, well, you can only have one instance running per process, for example, in the multi-process model. You can change that to a multi-threaded approach by simply having one instance running per thread. Right, so you have your components, everything is loosely coupled, things are really nice and really great. You can easily write your application using that approach. I've already talked about this slide, so I'm just going to skip it. And we're going to skip that one as well. One thing is very important. When you write the component objects, you should not keep state in those objects. Because those objects usually are singletons and they only exist once in your application, you should try not to have anything in there that well, basically changes the behavior of the component with the next request. So you have to separate the whole logic in the component from the data that you're using to process whatever you have to do there. questions so far? Am I going too fast or talking too fast? Is anyone understanding me? Yeah. All right. So this is a slide that has basically a big picture overview of how this can look. You have the various layers. You have components in those layers. This is a standard web application. So you have your requests, you have sessions users, you have the application logic. Usually factor out the presentation logic into a component. You want to do import-export, so you have a component for that. At the storage layer, you usually have database component talking to your database, or you have a file system component writing files to the file system. You can tie all that together. You can implement two-phase commits, for example, in the storage layer by having those two components implement the two-phase commit, so that you can make sure that whenever you process your request, that all the changes written to the database and file system are only actually done when you have a successful request. And on the side, you have this application instance layer that has generally useful components, like an error component that helps you with the error detection, error logging, and error handling. Usually you have a logging component so that you can set up your logging in various ways. And sometimes helps to have a debug component, so you have a central point where you can hook in your debugger to debug your application. Plus there's a special component, which is the system component. That is actually the application instance object that hooks everything together. And I'm going to talk about that a bit. So the way you set up an application is that you have one system component, you create an instance of that system component, and that system component will then create instances of all the other component objects you have in the system. And make sure that all these components are properly set up, hook them together, also does error checking. You can have components that only exist on a few systems. Say you have a POSIX system, then you just use one set of components, whereas on a Windows system you might use another set of components. So it makes it very flexible to adjust your application to whatever you're doing there. The system component object will usually also load the configuration of the application and use that configuration, of course, to configure the various components. Because it's just a single object, you can have multiple of these objects. You do have to watch out that you don't store anything in module globals, for example. So, because you want to have the separation really complete, you need to be very, very careful about storing things in modules, for example, dictionaries or namespaces that you have there. So instead of doing that, you should put everything, all the configuration, for example, into new component objects, and then just instantiate those component objects in the system component object, and then access the configuration, for example, via this system object. So in the application, what you typically see is you see an object, we usually call it just system, and that's the instance of that system component. The system component then has instance variables, one for each component that you have in the application. And if you want to access one of these components from anywhere in the system, you always go via this system object. So it makes it very easy to access the complete system from all the different components. And that's the basic idea behind hooking up the whole system. So everything goes via the system object. Okay, so we've broken down things quite a bit already. So we're now at the component level. The next level is breaking down things even further if the components themselves are still too complex. And we do that using management objects. Management objects, they help simplify the implementations. They provide APIs for various things, for example, file I/O. The management objects know about certain concepts that you have in your applications. they provide a simple API, usually just a few methods, which is what the outside components then use. They never go directly into the data that the management objects provide. And they help encapsulate all your logic that you have in your application. One thing to note is that the distinction between management objects and components is not always clear. So in recent projects we just have management objects, so we didn't bother with the calling them components or anything. It's not always. It depends a bit on the size of the project that you have. If you have a huge project, then it's probably better to have this distinction between components and management objects. For smaller ones, you can just fold them into one type of object. So the management objects are the objects that actually work on the low-level data and task objects in your application. They deal with the raw data. So we've reached the lowest level. Yes?
Do you mean that management is not based on the component objects?
Sorry, I didn't.
Do you mean that management objects are responsibilities based on the component of the component object that are doing a lot of complex algorithms?
Well, the components usually have complex tasks to implement. For example, if you have a database component, well, it sounds very simple, but in reality it's often a very complex task that's going on there, or multiple tasks going on there. So in order to manage those complex things, you split that up again into smaller parts. It's actually very much like what you have in life. When you look at the company, you have a company, you have divisions. Divisions have managers, and if the company is big enough, you have management levels under that. And at a very low level, you have the workers, and they do all the work, and management is happy. So the application design basically works much in the same kind of way. This is the same kind of approach. Right, so if you go down to the lowest level, you have the data objects, nothing really new there. You have task objects that know how to do certain little things, and you put all that into Python classes, and then have the management objects work with them. So this is a typical example of how the communication works in an application. You have down here you have the data and task objects. For example, that's a task object doing an export, and it wants to do something. It wants to write an XML file somewhere. So what it does is it simply goes to the management object, to the handler, up to the system component, and then goes down again to the import-export component, and through the export manager to the XML export. And that actually does the export then. So everything, it's basically a tree that you have there, and everything goes by the root. So the paths that you have in your application are very, very short. They're not direct, because you don't want to do direct connections. You want everything loosely coupled, so you can replace certain things, which is why you always go by the root. But it's still a very short path, and you normally always cache the system object in the task manager, for example, or in the management object. So it's really a very direct way down to the other components and management objects. One thing to note, if you write an application like this and you get a traceback will not be your usual 5-level traceback or 6-level traceback that you find in Python. The traceback generated in these applications, they usually have 20 or 30 entries. So it really goes very low down into the stack. So you have lots of nested function calls in there. But that actually makes things a lot easier to handle, because you can always see on the stack trace the various levels at which certain things got processed and how they got processed. So it's also easier to detect the origin of the error. Okay, so for web applications, what you usually have is you have a request, you have a response. Probably all know that. In the context of this kind of design where you have the components, this request object becomes very important because, like I said, you don't try not to store any global data in the components. Instead, what you want to do is you want to keep all that data in special data objects, and you pass around those data objects to the various components. And for web requests, you usually have a request object which stores the data from the incoming web request, and you associate with that a context object that has all the context of processing that one request. So as the data flows through your application, you often have to add extra data to this context object. You have to process the data that you already have in the context object, and you want to be able to pass data back to the response object in the end. So you keep all the global data that's only specific to that one request in this request context object. So it's a special kind of data object that you have. And if you use this kind of approach with one context object on each that you usually have as parameter in all the methods, then you've pretty much solved the issue of not storing any request data in the components. Right, and like I said in the beginning, there's beauty in design. So if you look at your design and your code there, if something doesn't look right, it looks ugly, then it's very likely that you've done something wrong, and it could probably be done better or made easier, because Python really encourages you to write nice code and nice structures. Right, so this was the second part of the talk.
Question?
Yes.
Is your system component some kind of really something like inversion of control container?
The inversion of control container.
Dependency injection pattern.
It is
It's
something
not popular in Java world.
Yes,
for
but
example.
it's not really. It's really just a very simple kind of object, and it just has a few pointers to the other components. It doesn't do any work by itself, right? So it only references all the different components in your system, and does a bit of startup and shutdown processing, and that's about it. There's no, you don't have a control structure in there. It's nothing. The system component doesn't do any specific processing on whatever you're doing in the system. Does that answer your question? More or less, yeah. Right, so it's 10:15 now. We can have a discussion now, talk about the things, or I could continue and then maybe go into the break, or I could offer a breakout session as open space. What do you prefer? Yes? Okay. So the second part was mostly about the design process. It's a bit hard to explain sometimes. It helps when you actually sit down and start to actually do these things. However, it's very important to first think about the design of the application and then start writing code. Because, especially in Python, because it's so easy to just start writing applications, people often just sit down and start writing code and then think about the design, which is the wrong way. So, especially if you want to create larger applications, so you always have to sit down first before you do something, think about it, maybe even twice, it's often better. And when you find that you don't see any immediate issues in your design, then you start writing code. So experiment. So this part of the talk is basically just a few recommendations that you should use in your coding to make it easier to maintain the code. Because if you have a few 100,000 lines of code in Python, it's just as hard to get an overview as a C application or a Java application. It doesn't make any difference anymore. So one thing that you always have to avoid is don't do this wildcard import. It's probably one of the things that Python should have never introduced in the first place. Instead, always use absolute imports. Put them all at the top of your module so that when you're reading a module, you can directly see the dependencies of the module. And by using absolute import paths, not relying on relative import paths, and not using the new feature that we have in Python where you can use this little dot for relative imports, it will really save you lots and lots of hours later on in debugging the application. There are several issues with not using absolute import paths. A very common one, if you use pickle, for example, is that you can have the situation where when you unpickle something, you get two different classes, and then your checks like isInstance, for example, don't work anymore. Because isInstance does an address pointer check, and this can be the result of these imports. Next thing is, well, fairly obvious nowadays. It wasn't obvious when I wrote these slides, which is a couple of years back. You should always use Python packages if possible. Sometimes you run into situations where you have import loops, so you want to import one module, and that module then has a dependency on the module that's importing it. You can work around that by using startup code. What we usually do is we have the imports then, if we have a situation like this, only in that case, because it's not a very nice way to do things, having an import somewhere deep down in your code. What we then do is we put the import into the startup phase of your component. And you can work around these import loops. Finally, the right package structure is a bit more complicated. What we typically do is we just look at the model decisions we made, and then just name the directories after the various model components. So we have a server directory, a client directory, then we have a directory for all the different components, and we have the management objects then as Python modules in those package directory, the Python packages under the component directory. If you have data and task objects that are associated with only a specific management object, you should put the implementations of those objects either into the same file as the management object, or better, probably, put them into a separate module and into the same directory as the management object. So you can immediately see the structure and dependencies when looking at your directory dump. It's also important to keep the modules small. So it doesn't really cost anything just creating a few more modules, because they're just files on the file system. And later on, when we're working with these modules and trying to find something quickly, it helps a lot. Another suggestion that I'd like to make is to always use data objects for the data that you store. It's usually better to not use symbol types for storing data. The reason is that you can very easily add new methods to these data objects. Performance-wise, it doesn't really make much of a difference. Nowadays, you can subclass directly from tuples, for example, or lists, so it doesn't really cause that much overhead. And for extending the application or changing certain aspects of the application, it's much easier to just have a data object there and then use that instead of trying to work everything into a tuple, or, I don't know, changing the number of elements that you have in a tuple or a list, or using a dictionary to map certain things. And we found that namespace objects are very useful in this respect. So in many applications we use namespace objects that basically just provide a standard Python namespace, more or less like a dictionary interface. You can just put data in there. You can have certain methods that do structured operations on those, on the contents of those namespace objects. And it's very easy to access the data in there using the attribute lookup. Something else you should consider is you should try to keep your methods very short, very simple. You should have a very simple API. It doesn't really make sense putting 20 parameters into a method call. Then you've probably done something wrong. You should probably encapsulate the data that you put in there as parameters into some data object, create the data object, and then put it into the call to the method. That also helps when doing debugging, because you have everything that's needed for that one particular method call in one object. You just look at that object instead of having to scan through all of the complete stack dump to try to find all the different parameters. You can use method groups if you want to implement more complex tasks. For example, if you have a database interface and you want to implement a certain aspect of data interfacing, you can group those methods. Or if you find that you need those groups multiple times, you can even factor out those method groups into mixin classes, which is a very nice feature in Python that you don't have in other languages because of the multiple inheritance that we have in Python. You can just add the mixin class to your base classes of the object, and then you just have the method group available. Does it makes it easier to understand because you can document the complete interface and what that particular method group is for in the class, and you can use that using automated doc tools. Also very important, do make mistakes, make lots of them, and learn from them. It's always, well, even if you try to do things right from the start, it doesn't work. It will never work. And it's nice that Python makes it easy to do refactoring. There are even some tools out there that help you with refactoring. It's very important to write the code, to actually use it, and when using it, to try to identify the certain things that don't work quite right, maybe don't look quite right. And even if you find that you have to rewrite 1,000 lines of code, it may well be worth it. Because in some cases, if you have complex code, by changing the design just a little, you can often have new code there that only has a few hundred lines instead of 1,000 lines. So it does really help. What you usually do is when you find you find that you have to debug some code, and you look at the code and see that it's just it's hard to understand. You can't really follow the flow of control in there and how the data goes through that code. It's usually better to just sit down a few hours and then rethink the design and then just re-implement it. Documentation is another important factor in the success of a project, because unlike many open source projects, it's not just one or two developers working on the project, but instead you have a whole group of developers working on the project. And what's probably even more important, developers pop in and pop out of the project, so they need to be able to come quickly up to speed with the code base, and so you need to write proper documentation for it. The way we do things is we don't try to write documentation in a way that makes it easily accessible for doc tools, or we don't try to put too much type checking and this kind of information into doc strings. What we usually do is, because we try to make things readable by the developer instead of some script or application running over the doc strings, we emphasize the important facts about all the different objects, parameters, and methods in the doc string for a developer, meaning a human, to understand. which is something that people sometimes don't really do when writing doc strings, if they write doc strings at all. So that's very important. Basically, the doc string is the contract that the developer of that part of code makes with the outside world and with the other developers. And if the method doesn't do what's described in there, then it's his fault. And if you change something in the method, then of course you also have to adapt the documentation for that. And ideally, you write unit tests to enforce this kind of checking. So you have documentation for the human to read, and you have the unit tests to actually check whether the implementation that you wrote there actually does what you wrote in that doc string.
It sounds a bit like I mean, what you're emphasizing is that you have like doc strings for making a contract, so that you can identify who's at fault if something goes wrong. And like unit tests are only optional. It seems to me like
no. Unit tests are for testing whether the stuff that you write in the doc string actually works as advertised, right? So let's put it this way: the contract with the other human developers, that's doc string. So that's a text that you write, and you want to write the text in a way that a human can easily understand it. Sure. Of course, you could also write it in a way that a machine could easily understand it, but that is like, for example, a doc test. Yeah. But that is not necessarily going to help the other developers, because it's not the format is so much different.
Let me just ask: are you going to have a slide about testing at all there, or is it just?
Yeah, there is.
Okay.
I think there is a slide there.
On the point of writing doc strings, did any of your developers use something like EuroPython to explore a large code base?
Right.
If you do that, you can put a question mark and see what that function does.
Right.
It speeds it up immeasurably.
Right.
Developing.
Yeah. Sure. I think the only point that I want to make here is that, well, first of all, write doc strings in the first place, because it's often forgotten. And the other thing is that humans read the doc strings and not machines. So, right. Another thing that you should always remember is to use this very descriptive identifier names. So it doesn't really make sense using one character variables in your code. And you shouldn't use abbreviations too much, because it's often hard to understand what you actually meant with the abbreviations that you use there. Today, editors make it very easy. They usually have auto-completion, so they just scan your code and know about all the variables that you use there. So you just hit Control Space or something, and then the editor will just auto-complete whatever you've written there. So it's not really an argument anymore that you have to type too much. So usually you have to just type a few characters and then you hit autocomplete maybe 2 times and then get your variable name, even if it has 20 characters. And that makes a huge difference also when reading stack traces, because all that you get there is you just get the variable name. You want to know what that variable name is supposed to mean. And then you can also see whether that variable maybe contains something that's not really meant to be in that variable. Right, quality assurance. This is the slide about testing. It's maybe the slide doesn't have a correct name. It's not really extreme programming that we're doing here. It's not this kind of pair programming where 2 people sit in front of the machine and try to write code. Because on the projects we typically don't have that many developers sitting there working on the same code. Instead, we have developers sitting on the various components and then writing code for the various components, so they're usually alone. But you can still apply some of the extreme programming techniques even if you're alone. What I usually tell programmers is to read the code that they write top to bottom without actually running it. It often helps when just going through all the lines of your code to identify certain bugs that you have in there, or typos, or you can see that certain code ports are not used, or maybe you've missed out some branch that is important. So you just go through the code, it takes a bit longer, and once you've done that, Then you start running it, and then you also write unit tests for that. So you try to identify everything that your code does or is supposed to do according to the docstring, and then you write a unit test that actually checks this. The first part of the slide makes it easier to identify bugs that you introduce when writing code right from the start, and the second part makes it easier to identify bugs that you introduce afterwards when maintaining the code or changing the code, for example, during refactoring. Because you always want to make sure that you don't change any aspects of the code accidentally just because you don't know what the code is actually supposed to do. Right, so I should probably finish now. Something else, typos are very easily made in Python because we don't have any really good tools to identify those typos. The best recommendation I have for that is use the editor's autocomplete function. That has two aspects. One aspect is that it actually it helps not making typos, and the other aspect is that it also helps finding typos. Because if you do it autocomplete and it scrolls through different options that you have, and you see one of the options has a typo in it, then you know that somewhere in the program there's a typo, and you can search for it and correct it. So that's one thing. The other thing is you can use tools like PyChecker, but they're not really, well, they can help with some things, but not everything. And of course you should always test the code before you commit it, but that's really something more about how you manage your project repository. So, okay, so we've had the structured application design process. We had the db.impera, which helps with breaking down complexity. And I've told you a bit about extreme programming techniques in a slightly different way to what you normally do. And I've already mentioned the fact that all this sounds very familiar, because if you look at it, it's very much like what you have in real life when running a company or structuring a company. The various aspects in the application work more or less the same way. Questions?
You mentioned that there were some programs which will help you restructure, refactoring your code. Can
Yes.
you mention them?
There are a few IDEs, like the Wing IDE, for example, for Python, that help you with that do restructuring. So you should have a look at those. Yes, there is another one, yeah?
What's your approach for logging? Do you use logging extensively in your applications?
Yes, we use lots and lots of logging. Logging is probably the best thing that you can do in an application, because very often it's hard to debug a live application, and it's especially hard after the fact. So if you have a stack trace somewhere in the application, and of course you need to identify where that stack trace came from. And so what we very often do is we put lots and lots of log statements into the application. We define various log levels. So during development, for example, we have a very high log level so that we log everything. And in production, we have a rather low log level. What we've also done is we've added code that doesn't only show the stack trace in form of just mentioning the line number that's causing the problem, but what we also do is we dump the complete locals in all the levels of the stack trace. So the stack traces in our applications are usually huge, but they contain so much information it's easy to actually identify and to see the cause of the problem.
And what logging facility do you use for logging?
We use mxlog for that. I'm surprised there, I guess. Yes?
I heard you say that you have your programmers working in the road area.
Yes.
So your programmers aren't really working together or sharing responsibilities? Or?
No, of course they're working together, but they always work on one part of the system. It's not like we don't have a set of programmers working on everything all the time. that also wouldn't really make sense because you want to parallelize the development. But of course we do, well the programs interact of course with each other and define, for example, the interfaces together.
So they do have responsibility for their own work.
Yes,
it's not
yes.
like one feature to be implemented by one guy in this thing, and the next feature from the same component could be done by another.
No, that wouldn't really make that much sense unless the component is really huge and you have to split it up anyway into smaller parts. But then you assign the smaller parts to the developers. More questions? Yes.
What do you use for debugging? For example, like interactive debugging, which is sometimes necessary in
Yes.
development.
Well, of course we use a debugger. Like for example, WingIDE has a good debugger that also works remotely. We use that, or we for web applications, because debugging web applications is usually very hard using a debugger. We tend to just rely on the logging, and if needed, we just extend the logging and then leave it in there. We don't take it out again. So we just extend the logging facility, rerun the code that was broken, provided we have the data available. Or we rely on these huge stack traces and just review those. So that's what we do for debugging.
So basically, for interactive debugging, you use the Wing, the facility provided by the Wing IDE.
Yes.
And have you tried, for example, Eclipse with its PyDef?
PyDef? No, we haven't tried that. WingIDE is a pretty good IDE for Python. So, I mean, PyDef is as well, but the problem is that you get the whole Eclipse stuff with it. Yeah. So you have 700 megabyte RAM process just when you start up the application. You haven't actually run anything, which is a bit huge even nowadays.
It's a really annoying model where you have to set up a project.
Right. Yeah. Plus the WingIDE guys are really friendly, so that helps as well. More questions? No? Well then, thank you.